So in natural languages, typically we have a sequence of text. So the structure is there linear. On the other hand, if you look at how the information is organized inside the sentence, so often it is there in some structured way, which is typically nonlinear. So parsing actually tries to identify that. In some other sense, parsing also tries to identify specific pieces of information from the input. For example, when you give a command line arguments to a program, so there is some parser that detects which argument is for which field, right? Similarly, in compiler also, when we look at sentences, there is a parsing that happens, and we get some kind of structure to identify whether it corresponds to the grammatical rules or not. Then, if you look at SQL queries, so there also the query is there, and there is a parser which identifies the different parts of the query that uh, connects with different constructs, and accordingly the execution happens. So parsing ideally is to identify the different components which are there in the input and how they interact with each other. So construction of sentence is governed by grammatical rules and how the words connect with each other according to the rule. So the structural composition of the sentence is given by parsing. So there are different types of parsing. One is constituency parsing, which gives us the phrase information. So in a sentence, there are multiple phrases. So how those phrases are there, what from where to where will be a specific phrase according to grammatical rule, and how these phrases are connected together to give the final appearance of the sentence. So that is given by constituency parsing. And dependency parsing tries to capture the relationship between words. And then there is semantic parsing, which deals with a logical interpretation. We'll go through these three types of parsing step by step. So to start with constituency parsing. So constituency is the fundamental notion that underlies the idea of constituency. So how things combine together, and it can be viewed as an abstract level. So group of words which behave as single unit, so they are constituents. For example, if you look at this sentence, on July 9th, I'd like to fly from Atlanta to Denver. So on July 19th, this is a specific piece of information which is being provided, and this can be a phrase, this can be an entire constituent. Similarly, from Atlanta to Denver, this entire piece is again giving some meaningful unit. And here the constituents for this larger phrase is from Atlanta to Denver. And the same information can be said in many different ways. And here across these three sentences, what we see is that they're trying to convey the same message. At the same time, the overall appearances of the sentences are different. On the other hand, some of the constituents, they are intact across the sentences. So somehow, if we are able to understand these kind of constructs, we may be able to get a better, we may be able to get the meanings of the sentence in a better way. So constituent structures can be modeled in using different kinds of grammars. So context-free grammars can also be used, and we'll look at some examples of that. So constituency CFG or context-free grammar can also be called as
Sir, can you please go to the previous slide? Yeah, just about this context-free grammar. So can you just explain it, Joe, how it will model this constituency parsing?
Yeah, as I said, we'll come to that. The next slides contain that.
Okay.
Please hold on. So CFG can be viewed as a device for generating sentences, and also it can be used for assigning a structure to a given sentence. So context-free grammar, I think people who have a computer science background may have had some idea about how or may have gone through the topic of context-free grammar as part of compiler course. So essentially, context-free grammar is defined by 4 parameters: n, sigma, r, and s. And what do they mean? N is a set of non-terminal symbols. So let me. So this is an example of constituency grammar. Sorry, context-free grammar. This is an example of a text-free grammar. So what we see is that this grammar is nothing but a collection of rules. Okay, so we have 1, 2, 3, 4, 5, 6, 7 rules, and these rules. What do the rules say? The rules say that okay, if you have this is a non-term. If you have s anywhere, you can expand it into ab. So suppose we have decided to generate a sentence, and we want to generate it following this context-free grammar. So the sentence will start with a start symbol s. Okay, and when we see s, it can be expanded as a and a followed by b. Then so that means s is a non-terminal which can be expanded into some other things. On the other hand, there could be certain words or terminals which are actual dictionary words. So the moment we see this Lec9 in Hyderabad, Bangalore, we do not expand them any further. So they are called terminals. So in this entire grammar, we see some production rules, and each production rule will have a non-terminal at the left-hand side, and the right-hand side will have a combination of terminal and non-terminals. And sometimes terminal might be missing, sometimes non-terminal might be missing. So this is what this formal definition captures. So R is a set of rules or productions. This entire, so 1, 2, 3, 4, 5, 6, 7. So there are 7 rules are here. Each of them is of the form A to some beta. So that's what we see. On the left hand side, we have one symbol, and right hand side, we have some expansions, where A is a non-terminal and B is a string of symbols from the infinite set of strings S union N star. So what is S? S is a special start symbol. This, every time it starts with S only. I mean, the sentence construction starts with S. And what is N? N is the set of non-terminal symbols. So in this case, the non-terminal symbols will be A, B, X, and Y. Okay. So, and beta is a string of symbols from the infinite set of strings S union N star. So what does it mean? The right-hand side can contain uh, can contain arbitrary number
Yeah,
of non-terminals, and you can
yeah.
I think sigma can also be included here. So S union sigma union N star. And right now, if you look at this grammar, it can also be written in a compact form as S to AB. Okay, this is the first one. For A, we have only one rule. A gives rise to 2x. So that's what we see. Now B to in Y. So that also we see here. And for X, we have two options, right? Hyderabad and Bangalore. So this can also be written in a compact form as Hyderabad or Bangalore. So X can expand into Hyderabad, X can expand into Bangalore also. Similarly, Y can expand into May or June, so which can be written in this manner. Okay, so this is an example of context-free grammar.
Sir, on the earlier side, sir, for non-terminal symbols, could you please once repeat again, sir, why D is not a non-terminal symbol?
Which one?
Sir,
Is
why
non
D? Okay, that is a complete
Oh, actually,
word.
Hyderabad.
Okay,
This
okay, got
Hyderabad
it.
is Bangalore.
Okay,
Yeah.
yes, sir.
Sir, I also have a question. Like we told that AB is a non-terminal, but
A and B are non-terminals. S, A, B, X, Y. So these 5 are the non-terminals here. And terminals, there are 4 terminals, 2 in Hyderabad. Oh, there are 6 terminals, 2 in Hyderabad, Bangalore, May, June.
but A is again expanded to X, right? So can we say that A is also a non-terminal?
A is non-terminal, yes.
Oh, okay, got it. And one question, like N and sigma, both are, one is non-terminal, and yeah, got it. Thank you.
So if we have grammatical rules, the English grammatical rules, which are properly and clearly articulated, we can get the parses of many different structures like this. So suppose we have the sentence John. So it can be noun, and a noun phrase can also contain a single noun. So this is one parse. Then suppose you have the student. So the is a determiner, which is an article, and student is a noun. And the grammar also has a rule: noun phrase can expand into determiner followed by noun. So that way we can get the parse of this one. Then it could be like the intelligent student, where the is a determiner, intelligent is an adjective phrase, and student is a noun. And the grammar will also have a rule like noun phrase can expand into determiner followed by adjective phrase followed by noun. So if you have the list of grammatical rules available with you, you can try to see how the sentence can actually be fit into those kind of grammatical rules, so that we can get this kind of connected tree. And but how to get that connected tree? So that is the parsing task that we are talking about. Similarly, there are a few others about prepositional phrase. So there is a rule from PP to P followed by MP, and from P there is an expansion to in. From NP there is an expansion to determiner followed by noun, and this determiner followed by noun, this determiner can generate the noun, can assume the value classroom. So together it can be there. So here that one level of parsing in this component has not been shown, and it has been shown in a compact way like this. Similarly, near the river, so it is a prepositional phrase. So this is one example, a larger grammar. So suppose we have the rules here and here. So these rules all deal with non-terminals or the variables. So S to NPVP. Typically in English sentences, we have the noun followed by verb. Uh, so the sentences which are of informative nature. So if we have the questions or interrogative sentence, the form may be different. But typically, suppose this is one rule, and there can be other rules also from S. So S to NPVP, and for NP, which is noun phrase, it can be a pronoun or proper noun or determiner followed by nominal, where nominal can be a nominal followed by noun or simply noun. Similarly, there could be rules for verb phrase and prepositional phrase. Now, noun, suppose it can assume the values lights, breeze, trip, morning. Verb, these are some of the values that it can assume. Similarly, for adjective, pronoun, proper noun, determiner, preposition, conjunction, and so on. So suppose you have these set of rules available with you, and the sentence is I prefer a morning flight. So you can see that if we get these parts, when all the branchings that we have here will come from some rule here. So S to NPVP, it is there here. Then NP to pronoun and pronoun to I. So that also we will have NP to pronoun is here and pronoun to I is here. Similarly, verb can give rise to prefer. So that we see here, and NP to determiner followed by nominal. So NP determiner followed by nominal, and nominal further expands into nominal followed by noun, like it is happening here, nominal followed by noun, and nominal to noun, and this entire thing can be constructed. So one can actually try to get these parts in a very brute force manner. Like you start with S and you keep expanding. So you expand S to NPVP, and then you see what possible expansions are there for NP. You see that, okay, these are the expansions. You take the first one, so NP to pronoun, and for pronoun, then you try to generate this and see does any of these match the terminal that we see here. So if we match, we retain it, and we keep continuing, we keep growing the tree. At some point of time, if we see that no further expansion is actually giving me the rise to a parse to this, we can backtrack. So this is one way in which parse tree can be constructed. That is called the top-down approach. And then there is some other way where you can actually bottom up, grow the parse tree from bottom up, and say I prefer a morning flight. This is my input. My first word is I. Let me see. Do we have any rule that says something gives rise to I? Okay, we see that, okay, pronoun is that thing. Now I and pronoun. Now in the left part we have pronoun, which is not connected with anything above, and then we have prefer, which is also not connected with anything above. So is there some rule that has pronoun followed by prefer? There is no such thing. Then we try to say, okay, for prefer, what is the other alternative? So we see verb, and like that in a bottom-up manner, it tries to grow the tree and connect these non-terminals to see finally if we are getting S. So again, that is a very tedious process. So I'm not going to, so that's why I didn't give detailed example of how using top-down and bottom-up parsing you can get these parse tree. So this top-down and bottom-up, this pure brute force method driven top-down bottom-up. So those things are not used for obvious reasons. So, and then there are some intelligent methods which, yeah, which can do it in a much more compact way. Now, when we say some method which can do it in compact way, that means that there's some automated algorithm, right? And that algorithm may give wrong output also. So how do we judge whether the algorithms are doing correctly or not, and so on? So there are different tree banks, which are data sets on which these systems can be evaluated. So tree banks are syntactically annotated corpus. Okay, so what does it mean? It means that you have a sentence and its complete parse as part of the data set. So this is the sentence, for example, that cold empty sky was full of fire and light, and the tree of that is given in this form. Okay, and the tags that are the non-terminals are these ones. So there are some other tree banks also. So there also we'll see some sentences and the trees, but the tags that they use might be different. So that is one thing to remember. So here what it says is that we start with S, and after S you see that a bracket has started, parenthesis has started. That means this is part of this S. Okay. Now for S, we have the expansion which says NP-SBJ. So from S, we have NP. And after NP-SBJ, you see that, okay, one more bracket has started. So what is following it is inside this one. So we have one more tag here, DT. And after DT, we have one terminal. So DT is giving rise to that one. Now you see this part is done. Next
What
we
is
see
SPJ?
subject.
Okay.
Then there is JJ hold. Now this JJ is inside a bracket. So it means it will be attached with whatever expansion we were continuing earlier. So this will be JJ. JJ is adjective. And after JJ we have cold. So JJ is giving rise to this terminal called cold. After that we have comma. So comma is separate type. Comma is also retained as a separate tag here. So this is inside the brackets, first thing inside the bracket. So we'll attach it to the expansion that we are currently doing. So comma, and this comma is giving rise to a comma. Then we have NN sky. So we have, so I made a mistake here. So
Sir, isn't
the
JJ should be
continuation,
connected to NP-SPJ?
so the so this starting bracket is inside this NP-SPJ.
Yeah.
So we are currently expanding this part. See, for NP-SPJ, this opening parenthesis that it has not been closed yet. So it's a parenthesis matching also which goes on between. So this will be connected with NP-SPJ. And this empty also will be connected with NP-SPJ. JJ, this will be empty. And then we have NN sky, so which is also connected with NP-SPJ. Then we have VP. Now this VP, this opening bracket, see, this parenthesis is matching with this. So this expansion is done. So this one is nested immediately inside this S. So now this one will actually get connected with VP. And like that, the tree can be constructed. So the tree form, which is a structure, has been serialized into a nested structure like this, something similar to what we have in JSON and other things. So if we have these kind of data sets, we can actually train our model, or even if our model is not a machine learning driven model, or rule based or heuristic driven, then also the output we can match against the examples here. So then there is this problem. Suppose we have a good model. Suppose we have model that can give parse trees really well. But then also there could be sentences for which multiple parse trees are possible. This is one such example. I saw the man on the hill with a telescope. So this is one tree and this is another tree. Why do we get two different trees? It is because the sentence can be interpreted in two different ways. One interpretation would be like, I saw the man on the hill and the telescope was the instrument through which I saw. Right? On the other hand, we'll have one more interpretation. We can have another interpretation which says that I saw the man was on the hill and the man was with the telescope. So that person was carrying a telescope. So, and both are actually valid interpretations. So we get two different valid parse trees out of this. Now, suppose we are told to, now how do we decide if our algorithm has to output only one tree, which one should we choose? So there is some ambiguity and we should have some way of resolving that ambiguity and saying that, or at least some kind of mechanism that says, okay, this is a way in which you can possibly assign some score to the different parse trees and you can output the one which has the higher score. So this is called syntactic disambiguation. So we'll look at disambiguation techniques after we cover the parsing technique itself. Okay, now we'll talk about one approach which is called as CYK algorithm. Okay, so it assumes that the grammar is in CFP. The grammar is in CNF. Okay? CNF means Chomsky normal form. So in context-free grammar, it is called context-free because in the left-hand side there is one non-terminal. In the examples that we saw only one non-terminal, right? So that part is okay, but from CFC to CNF, CNF puts an additional rule, additional restriction. It says that the expansions will be of this form A to BC, where B and C are non-terminals, or A to W, where W is a terminal. So any non-terminal can expand into exactly two non-terminals or exactly one terminal. And if you have all the rules following this property, then this is a CNF or Chomsky normal form grammar. So if we have something like, if we have something like A to Hyderabad, right? So that is not, if such a rule is there in the grammar, then it is not CNF, because on the right hand side we see two non-terminals, right? However, if we have a mix of terminal and non-terminal on the right hand side, even that is not a CNF. So this is a compulsory condition to be followed. Yes, I many scribble. So,
Sir, one question.
Hmm.
Here in CNF, both B and C are non-terminals, right?
Yes. The capital.
And if it would be CFG, then I mean, it could be terminal, non-terminal, or mix of both, like that, right?
You are right. Yeah.
Okay. Yeah. Thank
So CNF comes under CFG. So all CNFs are CFGs, but all CFGs are not CNFs.
you. Got it. Yeah. Thank you.
So we will look at one example. Tom sent the ball to the net. I'm trying to connect another device where scribbling becomes easier.
Hello, sir.
Hello.
Oh, I thought, sir, actually it is a network issue at mine. So
Okay. I'm trying to connect another device. This one I have to work out. I'll note down the grammar rules that we have. So S2 NP VP. Rule 1, Rule 2, NP2 det N, NP2 NPPP, then VP to VNP, then VP to VPPP.
So is there any first point because of messages it's not visible probably?
Say again.
But is there any first point you have written above NP to det N?
The first one is S2 NPVP.
Okay, yeah.
Okay,
Because-
it's not visible, sir, due to
Yeah,
the
there are
message.
some
read only.
messages. Yeah, so
But
You can close the message. You can
Yeah,
close
there's a
the message.
cross icon to close the message.
Then 6 is PP to PNP. 7 is NP to Tom. 8 is N to ball. 9 So these are the grammar rules. And we have a sentence to parse. That sentence is from sent the ball to the net, and we have to get the correct parse for this one. So we have 7 different words here. From is word 1, 2, 3, 4, 5, 6, 7. So we'll create a 7 cross 7 table. And so we have the 7 words here, and we have, that means now we'll add some markers to the boundaries. And suppose these markers are, this is 0, 1, 2, 3, 4, 5, 6, 7. Now let me erase the numberings with the words. We'll work with the boundary numbers. So so 0, 1. So now let us talk about some notation. So x 0, 1 will mean what we see between the boundaries 0 and 1. So which means it refers to the word Tom. Similarly, if we have x 0, 4, then it refers to the phrase Tom sent the ball. Okay? Like that. So we are marking the boundaries, and this is the sentence. At the very beginning, we'll start filling up the diagonals. Now diagonals mean x01 will be one diagonal. Now x01 is Tom, and we'll see, is there a rule that has x01 on the right hand side? So NP to Tom, rule number 7 qualifies. So we'll write NP to Tom, right? So rule 7. Let me also mark the entries here. So this is x01, this is x12, this is x23, this is x34, x3, sorry, 4, 5, x56, x67. Now this is for x12, this is x23, this is x34, this is x45, this is x56, this is x67. And here it is x23, x34, sorry, 0, 1, 1, 2, 2, 3, 3, 4, 3, 1, 2. Numbering I did wrong. The 0th row.
Start from 0, 0, right? I mean the matrix from form.
No, we use a different notation here.
Okay.
So this is 0, 2, this is 0, 3, this is 0, 4, 0, 5, 0, 6, 0, 7. Now this is 1, 2, this is 1, 3, this is x1, 4, this is x1, 5, x, no.
So I think in the second row, X12 is repeating.
It's 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 2, 3, 2, 4. So these numberings will be needed while we work out. 2, 5, x2, 6, x2, 7, x3, 5, x3, 6, x3, 7, x4, 5, x4, 6.
Sir, it should be 4, 6, X4, 6.
4, 6, 4, 7, 5, 6, 5, 7, 6, 7. Okay. Now, let us come back to the example. So x01 is the word Tom, and we have rule 7, which can capture that. Okay. Then x12, we will start from the diagonals. x12 is the word sent, and for sent, we have rule number 11. x23 is the, and for the, we have rule number 13. x34 is the word ball, and for ball we have rule number 8. x45 is the word 2, which is rule number 12, preposition to 2. And then the rule for the word 56, which is the, again we have rule number 13. And for 6-7, which is net, we have rule 9 as well as rule 10. So we'll add both of them. Okay. Mhm. Yes, it has come back. All right. Now what we do is we'll go to the above diagonal. So the main diagonal we have covered. Now we'll go to the diagonal which is comprising of x02, x13. So where we see a gap of 2 between the indices x02, x13, x24, and so on. Now x02 means what we see between the boundaries 0 and 2, which means Tom sent. Now for x02, we'll try to have some, we'll see between 0 and 2, can we break anywhere? And we have rules for those broken parts. So x02, we can break at one place, 1, and we'll have x01, x12. Okay, and x01 is what? Rule number 7, which is NP. Let me write the rule here. NP. So x12 is 11. 11 starts with V. x23 is rule 13, which is date. x34 is rule number 8, which is N. x45 is rule number 12, which is P. x56 is rule number 13, which is det. Then x67 is rule number 9 and 10, which means N and V. Now, okay, now x02, between 0 and 2, we can have 1. So we have x01, x12. For x01, we have NP. And for x12, we have V. However, we do not have any rule where the right hand side contains NPV. That means for x02, we will add blank. We will not fill anything there. Now let us look at x13. For 13, we can split it at 2. So x13 can be broken into x12, x23. Okay. Now for 12, x12, we have V, and for x23, we have det. Right? x12 is V, x23 is det. But we do not have any rule which has V det on the right hand side. So for x13 also we can store null or will not store anything. Now after covering x13, we go to x24. Now x24 can be split into x23 followed by x34. Now x23 contains det and x34 contains n. So do we have any rule which says det n? That is rule number 2, NP. So we'll write here NP rule number 2 in 24. And so what does it tell? So x24 stands for the phrase which is between boundary 2 and boundary 4, which is the ball. Right? So, and we are splitting it into x23 and 34. So the word the wall is actually being split into two parts, the and wall. So about the wall, this thing was together, and this entire thing we have now broken into the and wall separately. And we saw that. So what was the rule? We were looking at x24 and we broke it as x23, x34, right? And for x23, we had date, which is rule number 13. And for 34, we had end to wall, which is rule number 8. So this was known to be a date, and this was known to be a noun. And when we say that, okay, date followed by noun, which is rule number 2 here, that we are applying. So that means we are connecting date and n to whatever is the non-terminal on the left hand side for rule number 2, which is NP. So we are getting a partial parse for the sentence, for the phrase the ball. So there is some lag due to which the writing is not coming onto the screen immediately. But let us proceed with the next example, or next cell, which is x35. And for x35, we can split it into x34 followed by x45. For x34, we have the rule n, rule number 8, and x45, we have p22, rule number 12. P. So x34 is n, x45 is p, and we do not have any rule that has np on the right hand side. So which means x35 also will be blank. Then x46 can be broken into x45 followed by x56, and x45 as p and x56 has date. We do not have anything called on the right hand side, which is p followed by date. So x46 will not contain anything, will store null or will store blank here. And then we move on to x57. x57 can come from x56 followed by x67, and x56 we see that it has date, and x67 which has noun, which has two options, and we have to exercise both the options. So x67 can be n, and x56 is date. So date followed by n, we have one rule, that is rule number 2. So we'll write down np, rule number 2. And for 67, the other choice was v. Right now, do we have any rule that says date followed by v? No. So that one will not add any rule for the bucket 57. So we are done with this diagonal as well. Next, what we do is we'll go to the diagonal above. So now we'll start with x03. and x03, we can split into again two parts. So the first part, and then there are two choices, right? One is x01, x13, the other one is x02, x23. Now for x01, we have NP, and x13, we have nothing, right? So that means x03 cannot be broken at 1. And the other option is x02 and x03, x23. For x02, we have nothing. So we cannot have anything for x03. Next, we see for x24.
Sir, can you please repeat it again for the X03?
Again, which part?
Yeah, got it. This one. Actually, it didn't appear there.
Sir, how are you splitting X03? Can you please repeat that?
I couldn't get the audio clearly. Can you please repeat?
How are you splitting X03? If you could repeat that, sir.
So x03. Now 03 is the phrase Tom sent the, right? Now Tom sent the, we can break it into Tom followed by sent the, or it can be Tom sent followed by the, which means x03 we can split at 1, or we can split at boundary 2. So if we split at boundary 1, then x03 can be decomposed into x01, x13. If we
I think there's some network issue at source, and I'm not able to hear anything. Is it the same for everyone?
Yes.
So,
Yeah.
sir, if you are, yeah, sir, if you are able to hear us, we just heard when you were splitting X03 for 01 to 13. After that, we did not hear you, sir.
hello, can you hear me?
So
Yes,
now
sir.
we
Now
can
you're
hear.
audible.
Okay, okay. So so we were saying that x01, sorry, x03 we can break at 1 or 2. If we break at 1, we get two components, 01 and 13. And if we break at 2, we get two components, 02 and 23. So for x01 followed by 13, we see that although for x01 we have the rule NP, but for x13 we have nothing. So that means 01 followed by 13, so we cannot have this composition. Other option x02, x023 is there, but x02 actually gives you nothing, right? So even that we cannot exercise, which means we cannot have a valid parse according to the sentence for x03, which is the phrase Tom sent the. So 03 is gone. Now we have the next diagonal in that, yeah, so next cell in that diagonal, which is x14. Now similarly, x14 we can break into x12, x24, or x13, x34. Now we can see that x12 is V and x24 is NP. And we have one rule, rule number 4, which says VP to VNP. So for x14, we'll write down VP is the left hand side and which is rule number 4. Next, we have to see the other option as well because x13, x34 is the other possible split. But x13 is null. So this will not, this split will not give any valid parts. So we move ahead and we now look at x35. x35, so we break it as x34, x45. No, not x35, right? x25. So x23, x35 and x24, x45. For x23, we have debt and x35, we have nothing. So this split is not possible. And 2445 we can check. And there we see that x24 is NP, x45 is P. And NP followed by P, we do not have any such rule. That means for x25, we cannot have anything. So x25 is done. What comes next? Next comes x36. So x34, x46, x35, x56. X35 has nothing. And x46 also has nothing. So for x36 will not have anything. Next, x47, x45, x56, x45, x57, or x46, x67. So x45 is P and x57 is NP. So we have rule number 6, which says PP to PNP. So that is one possibility here, and we'll write down PP to PNP, which is rule number 6. And x46, x47. So there we see that x46 is empty. So that means 6. This rule cannot give us any further split. So we are done with this diagonal as well. Next, sir, we'll go to the yeah.
So one query just, sir, for example, here that is not the case, but for example, if there are two possibilities and we get the rule in both, then what we will apply? Will we mention both in the table?
We'll mention both like we have done for x67. So x67 is for the word net.
Okay, yes.
For net, we had rule 9 and rule 10. We wrote both. Yeah. Next one will be x0. Sorry. 4. Now see 0 to 4. In between we have 1, 2, 3. We have more options now. So more branchings are possible theoretically, but we'll see whether they are valid according to the grammar. So x01, x14, x02, x24, and x03, x34. Among them, let us eliminate the ones which are not possible, or let us go through one by one. X01 is NP.
Sir, one
X14
question.
is VP. Yes.
Can we have only two, like x01 and x14? Can we have 3 here, or only 2 is possible?
Only 2. So what? And this is why in the CNF we had the split like A to BC.
Okay. Oh, it's
so that is
understood.
breaking into 2. So here we are trying to break into two, and we are planning to assign one non-fit terminal for both the splits. So that's why that restriction was also put on the grammar.
Okay, got it. Thank you.
Okay. Now x04, if we split it into x01, 14, we'll see that x01 is NP and x14 is VP. So that means NP VP is on the right hand side. Rule number 1, which is S, is a valid parse for this one. So S, rule number 1. Now x02 has null, x03 also has null, so we'll not have anything from this. Now if you look at the sentence carefully, x04 is for the part Tom sent the ball, and it also looks like a complete sentence, right, according to the grammar also. So that's why we get the rule S here. Although, so if we only had the sentence Tom sent the ball, we could have got this as the parse. Next. So next we have x15. So x12, x25, x13, x35, x14, x45. So x12 is V, x25 is null. So it's gone. x13 is null, x14 is VP, x45 is P. And we do not have any rule which says VP followed by P. So x15 will store blank here. Next for x26, next we'll check for x26, and again the choices will become x23, x36, x24, x46, x25, x56. So x36 is null, so first rule cannot be there. Now 46 is also null, so this one also not be there, and x25 is null, so even this won't be there. So x26 will not store nothing here. x37, x34, x46, x35, x56, x plain average 7, 3447, 3557, 36, 67. So 34 and 47. 34 is what? 34 is N, and 47 is PP. Now NPP we do not have, so the first split is not possible, not valid. x35 followed by 57, but 35 is null, so it's gone. x36 and 67, 36 is also null, so even this cannot be there. For x37 there is no rule possible, so it's again a blank. Now x05. Now we have more split possible. x01, 15, 02, 25, 03, 35, 04, 45. Now x15 is null, so this is gone. x25 is also null, this is gone. x35 is null, this is also gone. x45 is P, and x04 is S. So we do not have SP on the right hand side. So x05 will not have any valid parts there. Our next contender will be x16, so which can be broken into x12, x26, x13, x36, x14, x46, x15, x56. But x26 is blank, so the first expansion is not possible. x36, x46 both are blank, so these two are also not possible. And then we have x15 as blank, so the last one is also not possible. So x16 does not give any further split. Next, we have x27, x23, x37, x24, x47, x25, x57, x26, x67. Now, among them, x37 has nothing. x47 has PP, but x24 has NP. So NP, PP. So we have rule number 3, which says NP to NP, PP. So in place of x27, one rule that will come is NP within bracket will write 3. x27 NP 3. Now x27 is what? The ball to the net. Two four four seven. 24 is NP, 47 is PP. Now 2557. 25 is blank. 26 is also blank. So the remaining things are not possible. x27 is done. And with that, we covered that diagonal also. Now we have x06. x06, x01, x16, x02, x26, x03, x36, x04, x46, x05, x56. So x16 is null. Then x26 is also null, 36 is null, 46 is null, and x05 is also null. So for x06, we don't have anything. Now x17, x17, x12, x27, x13, x37, x14, x47, x15, x57, x16, x67. Now x12 is V, x27 is NP. V followed by NP is rule number 4. Right? So in place of x17, we write VP rule number 4. So this rule. Now x1337, we see that 13 is blank, 1447, 14 is VP, and 47 is VP. 14 is VP, 47 is PP. So 47 is PP, 14 is VP. So VP followed by PP. Do we have a rule? Rule number 5. So we'll write VP followed by 5 as one of the options in case of x17. So V and P that give rise to VP, VP, PP even that is giving rise to. So x15, x57, 15 is null, then 16 is also null. So this is gone. So x17 is done. Now we have come to the last cell. Last cell is x07, and we can split it at many places. x02, x27, at 3, at 4, at 5, at 6. Yeah. Now x01, 17. So 01 is NP, 02 is VP. There are two rules and both are pointing to VP. Here we just write VP, and S to NPVP is one such rule, which is rule number 1. So this is there. 0227, 02 is blank. 0337, 03 is blank. 0447, 04 is S. 47 is PP. There's nothing called SPP. X05, X57, 05 is blank. X0667, 06 is also blank. So we have reached X07, which corresponds to the sentence Tom sent the ball to the net. Okay. Now that means since we have reached S, which is the start symbol, we have a valid parse for the sentence. And we did not write actually the splittings along with the rules in the matrix cells. So if we wrote clearly, we could have constructed the tree immediately, right? So we know for S, there the rule being followed is NPVP, and NPVP, and here the split is at 1. So Tom sent the ball to the net 0117. So if I just write the tree in the reverse manner, Tom sent the ball to the net x01 and 17, right? So this is getting connected with NP, and this entire thing is getting connected with VP. And this was x01, so no further split was possible. And this one was x17. Now x17 came from rules VP4 and VP5. Right? Now VP4, for that we had, so I have not noted down the split, but hopefully it will be send the ball followed by to the net. So that can be broken into send the ball and to the net. And sent the ball means 1 4. X14 is VP, and to the net is 47. X47 is PP. So this one is VP. This one is PP. So you can actually construct the parse tree from this table also.
Sir, there were two possibilities for X17, VP4 and VP5. Why we only
Both branches we can
consider?
have. No, we'll consider
Sorry.
both. We'll consider both. So we saw that there could be multiple parse trees for one input. Structural ambiguities were disambiguities were there. Sorry, ambiguities were there. So both will be considered.
Sir,
So
how do
will
you
that
break?
will that give rise to two parse trees then in that case?
Yes. Yes. I think there was something wrong here. So VP5 will not be, does not look like a valid parse. Let me just see 17, X17, X12. x17, x12, x27, x13, x37, 14. And 47. This is something that we have considered here. 1, 4 and 4, 7. And now 1, 3 and 3, 7. 1, 3 is blank. 3, 7 is blank. 1, 2 or 3, 7. 1, 2 is V. And 2, 7 is what? 2, 7 is NP. So the other possible split is 1, 2 and 2, 7. So sent and then the ball to the net. Sent is V, the ball to the net is NP. So that will be the other part stream.
Sir, can you
So
please repeat, sir, this at the bottom in the tree, how did we split that VP? Like send the ball to the net, how is it getting split?
So we had recorded that this VP so if we mark the boundaries 0, 1, 2, 3, 4, 5, 6, 7. So we didn't mark here, but algorithms during execution will mark that where we are splitting for getting that rule. So here we have 0 to 7, and we saw that for x 0 to 7, one rule was x01, x17, where x01 was NP and x17 was VP, another was VP5. Right? Let us focus on this VP, and this will give another parse tree. So is this part okay? That for Tom send the ball to the net, how are we splitting it into Tom and send the ball to
Yes,
the
sir.
net?
Yes, sir. That is clear. The below
Yes.
parts of
Right. Then we have now we are looking at x17, right? Send the ball to the net. x17. So when we did this, we had this one, right? 1, 2, 2, 7 and 1, 4, 4, 7. So we'll break at 2, we'll break at 4. So if we break at 4, this is what we get. Breaking at 4 means x14 send the ball, and then 4, 7 means to the net.
So while drawing the tree, we can do either or, like any of those two.
So this is one. We'll parallelly construct one more. We'll retain both.
Sure. Okay.
And yeah, so there are other ways. The immediately next thing is how we'll disambiguate. So that part will come immediately next. Okay, if we repeat this process, now here we have selected the first one. We can repeat that process. We can complete this parse tree. Once we are done, we can look at the other parts where we are actually breaking at 2, repeat the process and get that second parse tree as well.
Yeah, so just one more query here. Sir, do we always do this upper triangular matrix only here, or we'll complete the full like
Upper triangle is actually a dynamic programming algorithm, which is
okay,
happening
upper
here.
triangular. Yeah, got it.
So we decompose the problem into 2 smaller problems, and then we keep adding them, joining them. So for example, here we are parsing for x17, and the possible splits are we have listed down, and for each of the splits we have already computed what could be the valid parses there. So that's why we are starting from this diagonal and going towards the upper triangular. If you look at the diagonals, any diagonal, you will see that the length is same. So x01, x12, these are in one diagonal, right? So the length between the indices is 1. So that means we are looking at phrases of size 1. Now the diagonal above is x02, x13, x24. Gap is 4. the gap is 2. That means we are looking at 2 words. So X07 is a complete sentence with 7 words. So when we split it, we get smaller fragments. And for the smaller fragments, they'll be there in the diagonals below it. So that means for computing for a cell, we need to have all diagonals before it, all diagonals below it already computed. So that's why we start with the main diagonal and go upwards.
So sir, in any circumstances, the root node, which is here x07, which will always have some rule, right? It will never be empty.
If the sentence has a valid first, then yes.
Oh, so if it is empty, then how do we break it? Like root node itself is empty now.
We don't break. The sentence does not have a valid first according to the grammar.
Oh, okay.
Okay, I hope the algorithm is clear. So it was a bit verbose and working out took time, but I believe the central idea here is clear. Now let me.
Sir, one question. So is it possible the root node like the X07 can have multiple like the ambiguity thing?
Yes, it can have. See, S also can have multiple expansions. So let me stop sharing this and we go to the slide. If you look at
And so the number of ambiguities is equivalent to the number of trees that it would basically we'll come up with.
yeah, we don't call this a number of ambiguities, but yeah, number of ambiguous parse trees will be that. It can be more than 2 as well. So here, if you look at this grammar, not in this grammar, but there can be grammars where we have multiple. So are the slides visible?
Yes, sir.
So this one. So for S, there can be multiple expansions. So for X07 also, you can have multiple S's on the parse trees which differ from the very first place.
So in that case, like if root will have ambiguous, so then we'll have multiple rules for the root, right? Is now we have NPVP, so there could be some other rule.
Yes. So anywhere you see multiple rules, it will lead to a multiple parse trees. Now that anywhere those multiple rules can be anywhere. It can be at the top, it can be at some intermediate level, anywhere.
Okay.
So if you look at these two sentences, so here both start at NPVP, but you can also think of sentences that do not have any noun phrase to start with. Say, bring the pen. It starts with the verb. So there is no noun. So S to NPVP will not be. So there could be rules, and yeah, it can start at the beginning.
How do we design these rules, sir?
These are given. So we assume that these are given to us. This grammar is given to us. And then if there is a grammar which is not in CNF form, then we can actually convert it to CNF very easily. So let me show you one example of that.
Sir, I think Abhinav and Samir have their hands up.
Yeah, I will ask you the questions after this.
Yeah, Samir, any questions? Or Abhinav?
Yeah, sir.
Yes,
So
sir.
these rules, yeah, Vino, please go ahead. You go first.
So, in the time complexity part that you have mentioned for the CYK algorithm, it is order of n cube into length of the grammar. So, in the example that we had discussed, it was length of the grammar is 14.
Number of rules, yes. N is the number of rules in the grammar.
Okay.
Sir, regarding
suppose-
the rules, yeah, sorry.
No, go ahead, go ahead.
Sir, you mentioned the rules will be given. So are these like standard rules for CQ algorithm, and do we need to memorize this to solve any problem?
Not no. So for different setups, there could be different rules. So for example, if you have a say SQL query, right? The rules are defined. Those are very elaborate, but those are defined. So in these data sets also, the rules are given and the sentences are given. So in that sense, those are available.
So there will be only one rule for a whole data set, or it can differ on the sentence or document wise.
We saw 14 rules here, right? So the grammar can have multiple, I mean, have hundreds of thousands of rules also.
Yeah,
So it
that's one
expands
set of rule. So those 14 rules are one set of rule. I was asking, can the set be repeated? Like, can we have 2 or 3 set of rules?
I don't see a reason for that unless we are mixing, say, SQL query and natural language query kind of thing.
Okay.
Unless the domains differ, I don't think the sets will differ.
Okay, got it.
Now suppose we are having a yes. Suppose we are having a grammar which says that A to B C D, B to X C, C to Y, D to Z A. Suppose this is the grammar. So do you think it's a CNF?
No.
No.
So can you identify the productions due to which it fails to be a CNF?
2 and 4.
Yeah. So, X and Z are the terminal symbols and which occurs with the non-terminal symbol.
Anyone else with any other response?
And also A to
one
B, C, D is there.
One as
So
well.
1, 2, and 4, all three actually violate. Now suppose we want to convert it to a CNF. We want to convert it to CNF. Now this is CFG for sure. Left hand side we have only one terminal, only one non-terminal, and right hand side we have combination of terminal non-terminal. So this is CFG, yes, but CNF, no. So we can simply, this A to BCD is there. We can make it as A to A1D, another symbol we are introducing. So this we are doing to make sure there are two non-terminals on the right hand side. And let us write A1 to BC. Now these two together will cover rule number 1. Okay? And then rule number 2 is there, which is B to XC. But again, this one, suppose we have B to capital X followed by C, and capital X gives rise to small x. Rule 2 is also covered. Rule 3, yes, as it is. Rule 4, similar to what we did for rule 2. So that Z, so we have a mix of terminal and non-terminal, which is not allowed. So this Z, we make it as a non-terminal. Now this is a CNF and this is also a CFG. And these two grammars are equivalent. So if you have any grammar which is CFG but not CNF, you can actually convert it to a CNF. Okay, now let me go back to the slide and cover the next part. It's 9:30. So I'll just cover the disambiguation part, and then we'll go for a short break. So the algorithm will look like this: CQI parse. From J from 1 to length of the words. So in this case, it was 1 to 7. For all A, that's for our rules, where the left hand side is. So these are the rules actually. For all A such that A to words J is in the grammar. So we are filling up the diagonals. So if you remember in the first case, we just look at individual words and then fill up the diagonals. And individual words are the terminal. So that's why A to words J. So for all these rules which are there in the grammar, table J minus 1J. So we had 0, 1, 1, 2, like that, right? So there we add in this rule. Look at this union, which says if there are multiple rules, we'll add both of them. And then for I from J minus 1 down to 2, K is I plus 1 to J minus 1. So what is happening here is we are looking at the cells Ij and we are splitting them at K. And K is between I and J, right? So 0 to 4, we saw that the splitting points could be 1, 2, or 3. So K will be between I plus 1 and J minus 1, right? So I to J thing, if we break it at K, then we have two parts, Ik and Kj. So this next part is actually trying to see if there is a rule. So if we have A to BC, where B matches with Xik and C matches with Xkj, then that rule A you add to that cell. So this is exactly the algorithm that we have followed. And if we want to disambiguate, what we will do is for each rule, we'll assume that a probability is there. So this is one example where S can expand into multiple things. So S do this. Now, these are the probabilities. So if the left-hand side has S, then this rule is taken 80% time, this rule is taken 50% of time, this rule is taken 5% of times. So these are the rules associated with the probability. Similarly, for NP, there are 4 such rules, and these are the probabilities with which each of these rules are taken. And these rules, where NP is there on the left-hand side, will actually sum to 1. So these probabilities tell if the left-hand side matches, what is the probability that each of the rules are taken. Now, how do we get these probabilities? Using those tree bank. In those tree banks, we see in how many cases NP expanding into rule 1, rule 2, rule 3, rule 4, and accordingly, we decide the probabilities. Now, when we have the probabilities, we can do this parts in a greedy manner. And what is that greedy manner? So this part is okay. Firstly, we fill the diagonals, and then suppose this part is also okay. For I to J, we are identifying the splitting point. And now we are saying that I to K, for this, we have rule B. And according to the, along with the rule, earlier we said, along with the rule, we'll write the rule number and the splitting point. Now we say we'll write the rule number, the splitting point, and also the probability. So IKB, so that probability is greater than 0. And here also this probability is greater than 0. That means none of these entries are null. Then we compare the table IJA is less than the probability that this rule can be taken and the rules of these individual probabilities. So this entire product we compare. Now, if the probability for this current rule is less than this entire thing, Then we replace the current rule which is there by this one. So what does it tell? It tells that, or suppose we have the tree grown like this, and sorry, this. So we have, say, xi k and x k j. So this is nothing but there is a parse under this, there is a parse under this, and we are combining these two parses using a rule which says, so suppose this rule is governed by B and this is by C, and we have a rule A to BC. So this rule will have a probability P1. So this we get from the table. Next, each of these parses will also have their own probabilities. So we're doing it ground up. We're doing it in bottom up manner. So every cell, every time we fill up a cell, we get the parts for this probability for this corresponding parts. Suppose this one is P2 and this one is P3. So the probability that we see this entire parts is P1, that this rule is taken, into P2, that is this parts is valid, into P3, this parts is valid with probability. So these three things together determine the strength of these parts A to BC, where B is for this and C is for this. So this is the new rule that we are exploring. And if this one is more than the entry which is there in the table, then we replace the entry by this probability, and yeah, this back ij, this is the for reconstructing the tree. For ij, A was the rule, the constituents were B and C, and it was split at Q. If the probability of the current parts is more than the probability of the existing parts at this cell, we replace. Otherwise, we continue with the previous one. So this way, that exact same algorithm can be used with minor modification. It's not exact same, but yeah, algorithm with minor modification can be used.
So are we saying that we are basically finding out that which of the two possible subtrees can be having more higher probabilities, and we'll be taking them?
Yes, yes. So suppose we have these rules, and our idea is that we'll choose the parse tree with highest probability, and we're doing it in a greedy manner. And suppose these are two parse trees which are possible. The algorithm, if we didn't do the parse tree computation, the probability computation like this, suppose we had got these two parse trees. Now each of these parse trees, the probability associated with that can be computed as the probability of each expansion that we are seeing, each branching that we are seeing. So S to VP is the first branch. The probability is 0.05, and VP to verb NP. So this one. So probability is 0.20. So like that, for each branching, we have the probability that, and since each of those branchings is there, so the total probability of the parts will be a product of those. Right? So for these two trees, we can compute the probabilities, and the one which is more that we can retain. And so if we have output that we,
it is kind of a top-down pass we are doing, right? So, but earlier we were saying that we are doing bottom-up. So I was just not, that less than part I didn't understood. P to AB, and it should be greater than, or
what in
in
the
that
algorithm?
pseudo code, that part that we shared. Slide. So this is the A is the root node, right? And we are having the leaf would be BC or B and C, right? So
So it's very similar to the CQI parsing. So Tom sent the ball to the net, right? Net, then the net, then to the net. Like that, we started combining things, right? We're doing it in roundup manner. Suppose for x 0, 4, we can split at position 1 and we can split at position 2. So we are filling the entry x0, 4. Initially, there was nothing. So if the split at 1 is taken, there is certain probability. So fine. Now we evaluate for split at 2. Now suppose when we evaluate for split at 2, we see that now the probability that we get is higher than this probability. Now we replace. Now suppose there is another split is 3. So this will be replaced.
Okay, so basically the root node value is getting updated by the the subtree values which is getting the most. Is my understanding correct? On the basis of the subtrees probabilities values, the root node values are getting updated.
It's not the probability, right? It's the rule itself which is getting updated.
But it's the probability we are storing, right? At I, J, and A.
I understood that from probability, we decide that either left or right, which one rules we are going to take. In earlier case, there was possible like split is there at the 2 and 1, right? Now we see that which one has the more probability, and then the one which has more probability that we take in the root node, and the probability of root node we decide or calculate as per the rules given in the table. I'm not sure that's what I have understood till now. So it seems like in this case, there will be only one tree. There won't be any ambiguity.
Hello?
Yes, sir, we
Yes.
can hear you.
Mm-hmm. Okay, so is it clear or there is some ambiguity here?
Sir, we need a little more like what I was thinking is in this case, like once we have two branch left and right, and we see that which is having more probability, that rule is getting updated to the root node. Is that correct?
Not root, but yeah, till what point we have reached till then.
Okay, so that part where we discussed that according to the probability, we replace the root node. So my question is that how are we replacing the root node, or we are taking the rules itself to the root node from left or right?
So
And how do we
in this
calculate
case,
the?
only one parse tree. It will output only one parse tree. It will also maintain only one parse tree.
Yeah, so there won't be any
Only.
ambiguity.
Yes. So this is PCFG for disambiguation. Which is also so it will replace the existing rule. It will replace the existing grammar rule with a new one.
Yes, got it. And this probability, how these probabilities are calculated? Is it like predetermined, or we find from the data set, or it's given?
So as I already mentioned, it can be computed from the tree bank. In the tree bank, you see how many productions of these rules and how many times each of these occur. So probability of alpha to beta is how many times alpha to beta this branch is taken among the ones where the left hand side is alpha. So if in the tree in the tree bank, if you have 1,000 examples, where, I mean, not 1,000 examples, you have 1,000 times this, where the left-hand side is NP in this rule. Out of them, how many times this is pronoun? How many times this rule is followed? How many times this rule is followed? So like that. So based on that is a count-based estimate. You'll get this one. So that's why
first
this
we
part.
create, yeah, that part we understood. So first we create the tree and then we decide the probability, and then according to the probability we update the rules.
Here.
Yeah, so first we create the tree using methods we discussed. Okay.
This is a data set where you have sentences and the parsers.
Okay.
Okay. So that is for citing this, and I'll touch upon one neural algorithm for this one. So here what it says is that, suppose this is the sentence, the cat on the mat. So for each word will have its representation. It can come by any means. And at each and every time we'll try to join the current node with the next node towards the one which is towards the right. So for the and cat, what is the strength of this connection? So that will be given by a neural network. Then cat and sat, these two we consider what is the strength or what is the score if we combine cat and sat. Similarly, sat and on and the and mat, and these are actually denoted by these merges. Okay, and suppose for this neural network, when you give the input the and cat, it outputs 3.1, and these are the instantiation of the same neural network. Okay, 3.1, in this case it gives 0.3 and so on. So we'll pick the one which has the highest. So here 3.1 is the highest, and I mean, at one step you can do one merge, two merge, so that depends on the algorithm. Suppose we decide to merge the highest only. So this 3.1, since it's the highest node, highest score, so we'll merge the and cat, and we'll get one node. Okay. And this node's representation will also be given by this neural network. So now we'll have that on the mat as leaf nodes, and we have got one intermediate node, which is the combination of the and cat. Now we repeat the process with this node and these four nodes, and step by step we construct the tree. So this is what we do. Suppose riding a bike, these three are three words. So they also use the, yeah, for riding, suppose this thing is verb, the label is verb, and for A it's determiner, for bike it is nominal. So parse tree construction in recursive manner. The next two nodes to be combined is decided based on greedy choice. For each pair of consecutive nodes, find a score. So here we'll be finding score between ride and bike. Pick the pair with the highest score. So here, suppose in this algorithm, a bike that had a higher score. So we pick this one. Merge them and replace the two constituent nodes with these merged nodes. Okay, so we have one merged node here. So, and the scoring, they propose this formula where A and B are the representations for the two constituent nodes. For example, A is the representation for this and B is the representation for this. So they combine them, multiply with a weight matrix, add a bias, and then pass it to a neural network. So you get something here. And also they add probability for the rule XAB. So see here, there is one matrix for each AB. So among all possible choices of AB, among all possible choices of the rules, the one which gives the highest value, so that will be taken. So schematically, so this was there. So suppose these two were merged, then these two were merged. So like that in step-by-step manner, this will be constructed and we'll get the final parts.
Sir, in the previous example, so how we are getting the first writing as a separate unigram token in the first instance only? Will not it be always a first merged sentence merged thing would be bigram token? Basically, I just want to even if we apply the same recursive part to this a bike, so how we will be able to get the A as a separate token and the bike as a separate.
So anyways, we start with everything as a leaf node, right? So everything is a separate token. And then the rule has to generate the word. So riding, it comes as a verb. So there is no other choice there. It will be there.
First,
I mean,
first for the first sentence, riding a bike was merged, and then riding was a separate had the less probability for with A riding A, so that's why it was separated, right?
right,
If I
right.
understand.
Right. It makes a sequence of greedy choices.
Sir, how do we train this network? What's the loss function there?
So here the loss function could be like the probability of the tree that you get by multiplying all this and the probability of the ground truth tree. So based on that, loss function could be there. So from a paper, I'll give you the link to the paper.
It's
Yeah.
probability of the leaf node, right?
Probability of the parts. So once you generate the parts, at that point, you compare that with the ground truth parts. And the loss function could be based on the probabilities of these two parses.
So, so is it a feed forward? So, for example, once it determines one, then the output is again passed to the other one and then combined, because that way we have to. It can be of any order.
The complete parts is obtained, and then you, yeah, even an input, you obtain the complete parts, and then only you compare with the ground truth parts. You delay the loss computation till the point the complete parts is obtained.
And it's the same network, right, in which we pass all the inputs.
Yes.
Weight is same. So we keep calculating the output and we keep the probability and then we multiply and then we compare it with the ground truth one for each and every node. Is that the case?
This network remains this is the same network. Across iterations also it will be the same network until you obtain the parts, complete parts. Then you update, parameters get updated.
So for loss, do we take in the account of all these nodes, the probability, or just the final root node probability?
Probability of the parse tree. So suppose this is
All
the
the
input and pass it through the algorithm, you get a parse tree, and then there is a ground truth parse tree, and then you compare.
Yeah, got it, sir.
Sir, is this the bi-RNN that we are using that greedily?
Anything can be used here. The simple neural network, you can use anything. Okay, and this anyways was covered like the partial parts or chunking. So when Srijit covered sequence labeling, this part was there. So there could be some parses where we are not interested in the structure of the complete sentences, but the important pieces of information. So named entity recognition or pause tagging, they fall under this category. So suppose we say, okay, these are the things that we are interested in. So that leads us to partial parse. So morning flight from Denver has arrived. Suppose we just want to identify the noun phrase, preposition phrase, and these things from here. So as long as we know these are noun phrase, these are preposition, noun phrase, verb phrase, we are done. We do not want to further identify the hierarchy of how this noun phrase is combined with this prepositional phrase, and finally we can get the complete parse, that root node S. So this is, and similarly, so this is called a partial parsing or chunking or segmenting. Now there could be situations where you have some sentences from a mathematical paper, and we'd like to identify the portion which is mathematical in nature. So suppose this is mathematical symbol, and this sigmoid function is applied on the output y equal to wxb plus b of the final layer. So this is math. This entire thing is math, and other things are, we do not care about that. We don't bother about that. So here, again, this is an example of partial parse, and BIO encoding can be used to get this labels, and you can train any sequence-aware classification algorithm to get these labels. Okay, so now let us go for a 15-minute break. So we'll come back at 10:15 and we'll take up the next topic, which is dependency parsing.
So thank you.
Yeah, so we'll resume, but some of you wanted so it's regarding the assignment, the second assignment. So in this assignment, it's actually for question answering. So you have to train a transformer-based model to answer multiple choice questions. And these are actually based on common sense reasoning. So there is a data set which is already provided. And yeah, so essentially in this data set, you have a question. And there is one correct option and 3 incorrect options. So these incorrect options are distractors. Yeah, so this is mentioned here, consists of a question, the expected answer, and up to 4 incorrect answers called distractors. Okay. The task is to train a model capable of identifying the correct answer among the distractors. And the dataset links are provided here. And there is a GitHub page also. So what you have to do is you have to read the dataset, understand the task. You may need some pre-processing of the data. I mean, there might be some additional columns that you may need to filter out. And yeah, train only on the train split. And if you think that the training size data size is too large that you cannot handle, you can actually reduce it. You can use a subset of the data for training, even that is allowed. And yeah, ensure that you do not use the validation or test data for your training. So this is the data set, but how you'll formulate the problem, how will you formulate the architecture, that's up to you. Yes, you are free to choose a model architecture of your choice, but you are not allowed to use any pre-trained fine-tuned model which is for this specific task. Okay, suppose you want to use BERT, fine, how many layers you decide, and that pre-trained BERT you can use. But the goal here is that you'll be training the network based on this task requirement. Okay. So pre-trained models are allowed, but usage of models which are trained specifically for this task, that is discouraged. And models can be customized as desired. So you can add more number of layers, activations, other things you can change. And yeah. Yes, so there are multiple options like A, B, C, D. You have to out which option is correct. And yeah, so metrics you choose. And finally, we want a short report. So your code can be submitted as an IPython notebook or Colab notebook, but we'll also expect a small report where you mention your findings while working on this problem. So yes, any questions here?
So one question, for these models, right? Can we use this Hugging Face libraries or?
You can use Hugging Face
I mean,
libraries,
not
but make sure. Yes, go ahead.
actually like a bird from Hugging Face, not like exactly as you said, like a model trained for this task. Maybe some general like a bird model or some other transformer model. So in general, we can use it, right? Like this
You
tokenizer
can
and models we can use from Hugging Face, right? Yeah, okay.
yeah. Feel free to use those.
So, but sir, we need to pre-train the model by our data in that case. Only the pre-trained models are not allowed. That's what you said, right?
No, pre-trains are allowed. Pre-trained models are
But
allowed.
we will have to fine tune it, right? And
Yes, but there might be models which are specifically pre-trained, fine-tuned for this particular task. Don't use those. Pre-trained BERT is allowed.
Okay,
So
the models pre-trained specifically for these tasks. Okay. They are not allowed. Okay.
Now, you tell me, when do you want to submit? What is a good deadline for this one?
So by the Viva time,
So the exam is on 27th. Should we keep 28th, which is Sunday, as the deadline?
So most of the people will be returning on 28th, maybe 1 or 2 days after that.
Maybe 29th?
Yeah, that
Okay,
will
so
left. And
Can
is
we
it
on
like
4th?
individual or like a group?
Can
it would be a group assignment, yeah, you did the previous one. Yeah, do it in the same
Okay.
group.
So set of two. Yeah, okay, sure.
Yeah.
can it be on 4th? By the way, I'm just asking.
No, evaluation will have tough time.
Okay.
So, sir, can we keep it like 30th, the end of the month, instead of 29th? Can we keep it like 30th?
So yeah, can you keep it like 30? That will be like helpful because I'll be returning on 29. That's why.
Yeah, same here.
Okay. Okay, so 30th, and that's a strict deadline. Okay. All right, 30th is fine.
Okay, sir. Yeah. Sir, what is the marks for this assignment?
We will see. We will see. It should be commensurate with the effort that has to be put in.
Okay, and sir, what is the distribution now? Because previously we had only one assignment, now we have like two. So what is the weightage at the end sem exam?
We can assume that some 20% will be for the overall assignments.
So 80% is on the end sem. Sorry,
No,
the quiz will be there also.
yeah.
So
So
end
20.
sem.
See, I'm giving you some rough numbers. There can be some plus minus 5% here and there. So assignment can be 20%, quiz can be 25 to 30%, and the remaining can be for the end semester exam. So 50 to 60 for the end sem, remaining will be distributed between these two.
Okay. I've said just one more question. You mentioned that pretend models are allowed. I have this confusion there. So pretend models mean BERT and those things are allowed, but pretend only for this purpose, for identifying the correct answer and incorrect answers. So this fine tuning models are not allowed. That is what you meant, right?
Right, yes.
Right. So we can take the pretend model and fine tune by ourselves. That is what you are saying.
Yes, and right, you
So,
can add your own architecture components.
so one example could be like, I mean, a llama model is allowed and code llama is not allowed. Like code llama is specific for the code. Similarly, for this one, whichever is specific, we should not be allowed, right?
So, right, I think yeah, pretend is fine, but don't take any model which is specifically designed and trained for this particular task. So there might be models which want to solve this task based on the SWOG dataset itself. So those things. Just 1 second. All right. Any other queries?
one more, sir. Is that best of two or best of three will be picked for quiz?
Quiz will be something like that. Yes.
Okay, thanks.
Sir, I have a question regarding that. We had a session related to the attention networks, where we had a code walkthrough, and so that transformer part is still remaining. So when it will be organized?
So some topics will be covered in the next. I don't think we have any other slot. Maybe if some weekday slot works, I'll ask the students to give a tutorial on that.
Yeah,
But
just
before
because the associated notebooks are also not shared, and the notebook shared is also not having. I don't have. I'm not having the access of it to download or to see it.
access to that will be giving. I mean, you could have told this earlier, no? That there is no access. So that access will give you.
Yeah, I will mail.
Only the owner can give, but yeah, you can let me know forward. Okay, so let us move on with the next part of today's lecture. Okay, next we have dependency parsing. Dependency parsing is, it deals with the syntactic structure of the sentence. The words actually depend with each other in terms of their function or meaning. So I'll give you one example. Suppose you have this thing. I preferred the morning flight through Denver. Here, the verb prefer is the root. Okay, and then how the different words are related, that information is captured here. So for the word prefer, the subject is I. And what do I prefer? The direct object is flight. And the flight has a modifier, morning. So it's a morning flight. And the word the is actually associated with the flight. So like this, the dependencies are there. Now, in case of constituency parse, you know that we are combining only the adjacent things, right? But here, these edges can actually go across the adjacent words also. So this is dependency, where relations among the words are expressed with directed as well as labeled edges. Now this is also called a typed dependency structure, and the dependency labels actually vary from dataset to dataset. On the other hand, this is the phrase structure grammar or the constituency grammar. You see that only the adjacent things are getting combined every time, but here it won't be the case. And I've given some links here for some demos that you can look at some later point of time. So dependency relation describes the role that the dependent plays with respect to its head. And there could be clausal relations or modifier relations. So what are clausal relations? Like what is subject, what is an object? So these are clausal relations. And modifier relations could be something like the nominal modifiers, the adjective modifiers, the count modifier, like two flowers or morning flight. So these kind of modifiers are, these are actually modifiers like morning, two, And on the other hand, if there is a clausal relation like subject object, so these come under the clausal relation. Then there could be conjunctions and other things. So this is another example. United cancelled the morning flights to Houston. So here clausal relations are subject and object, and then we have the other kind of relations. So here you have some sets of relations. Again, this is, as I said, these are data set dependent. Like United cancelled the flight. So United is a subject for the verb cancelled. So this is head and this is dependent. So arrows are always from head to the dependent. The labeled arcs from the heads to the department. So dependent. So the arrows start at head and end at dependent. So here are the things. Then we took the morning flight. So morning is the modifier, and there are quite a few others. So dependency tree is essentially a directed graph, as we have seen in the example. So it contains a set of words as its vertices or nodes, and the punctuations also can be included. There are many offerings that also include punctuations as the nodes. And then you have the set of arcs that captures the head dependent relation. So these are the edges in the graph. Okay. Now this dependency, it's actually a tree, but as we know, tree is also a graph. So that way we can also call it a graph. Now this is a connected tree, so will not have any nodes that is left out. It has single designated root node, the property that we have with any tree, and that root node does not have any incoming edges. And typically the predicate, that is the verb, so that the main verb, that is the root. Each vertex has exactly one incoming arc except the root. Right? Each vertex has exactly one incoming arc except the root. So each word that you see from here will have exactly one incoming arc, not more than, not neither less than that. And there is a unique path from the root node to each vertex. So from root node is cancelled, and from here, if you want to go to Houston, you'll be finding a path. So cancelled to flights to Houston. Now suppose Houston to morning, yes, again cancelled, then flights to morning. So for every node that you consider from the special root node, you'll find a path there. And there's also a concept of projectivity, which says that this dependency tree is projective if it can be drawn with no crossing edges. So suppose this is one sentence, and we see there are no edge crossings, right? So there is a projective tree. On the other hand, there are some sentences that irrespective of the way in which you draw the arrow, if you turn the arrow and come from behind, that's a different thing. But yeah, there is no way in which you can draw the arrows so that draw the edges so that there is no edge crossing. So if that is the case, then it becomes non-projective. So projective trees, no edge crossing. Of trees that are not projective, there will be edge crossing if we draw the dependency relations. So typically non-projective trees are very common in languages where word orders are very flexible. On the other hand, English has some very strict rules like subject, verb, and how the things are organized. So this is one thing. Now talking about one technique for dependency parsing. So we talked about this shift reduce parsing when we were covering rhetorical stored sentence tree RST structure. So this shift reduce parsing is used for dependency relations. So if you remember from compiler class, in case you have done a compiler course in your bachelor's, so it is essentially it maintains a stack. Okay, so next sentence, the next slide has an example, but I'll give the overview of its working. So the sentence to be processed is the input buffer. So each word is in one buffer. One cell, one position of this buffer. And then you maintain a stack. At the very beginning, the stack contains the root node. And this word list or the buffer is initialized with a set of the words in the input. And the goal an empty word list. So as we process, things get removed from the input buffer and certain things get added and removed from the stack. So finally, when we are done, the goal for configuration is that the stack should be empty, input buffer also should be empty. And when we look at each symbol, when we consume each symbol, there are three actions that we can take. One is left arc, other is right arc, and the third one is only shift. So what do they mean? So if we say that the action is left arc, then we have a head dependent relation between the top and the word from the buffer. So let me just correct this part. So head and dependent relation between top and top minus one. Top and top minus one. So it's a stack. So I mean, the word which comes first will be below and word which comes next will be on the top. So when we are adding from top to top minus one, that means we are adding an arrow which is going towards the left, right? The word which has already come. So that's why it is called left arc. And right arc means you are creating an arrow from top minus one to top. And then shift means you remove the word from the front of the input buffer and push it onto the stack. You don't create any edges, simply push the element. So, and how do we determine whether it should be left arc or right arc or shift? What is the operation? So the thing is that is determined by an algorithm. So that algorithm at the beginning, we call it an oracle, somebody who knows everything. So let us look at an example. Book the morning flight. So at the very beginning, the stack has only the root and word list has book me the morning flight. The action is shift. Okay. So root was there, book sat on top of that. So the stack has root and book and word list has these words. Now the first word is me. Action that was determined was shift. So me goes here and we're left with the morning flight. Now we again ask the oracle, what should we do? It says right arc. Right arc means top minus one to top. All right. So this is top minus one. This is top. So we have an edge from book to me, which is the edge added, and the position for which, which is the destination of the edge, that is removed. Why so? Because every vertex has exactly one incoming arc except the root, right? Every vertex has exactly one incoming arc. Now this word me already has an incoming arc, so it can be now dropped. So here we have root and book and the word list remain the morning flight. Again, we ask the oracle, what should we do? It says shift. So the word the goes to the stack. We have morning flight. Oracle says shift. We shift morning. Then only flight is here. Oracle says shift. We shift it here. Now the word list is empty, but the stack is not empty. So we continue. Stack is not empty. Final goal state will have the root only in the stack. So we have not reached the goal state. So we process this one. Now the oracle says you create a left arc. Left arc means flight to morning. So flight to morning, we have created an edge and then the target of that arrow, which is morning, is removed. So we have root book the flight. Now it says left arc flight to there is an arrow. And next we have root book flight. It says right arc. So book to flight there with an arrow. Root to book there is an arrow. So now we are done. So finally, if you combine all these things, if you note down the words and add these edges, you'll get this tree. So this is the tree that we get. Now the question is, are the sequence of actions unique? Answer is no. Here also there may be more than one path that leads to the same result. So actions may not be unique. Right? So there may be other transitions that lead to slight different but equally valid parsers due to ambiguity. So if the sentence has any ambiguity, the interpretation, the semantics also will have will be ambiguous, and the dependency relations also, it will be reflected in the dependency relations as well. So yes, but how to generate the labels of the arcs? So here we saw that only the edges are there, right? But these labels were not there. But how to generate these labels? So you can again modify your algorithm which predicts the action, and it says right arc, comma, the label. So it may say right arc, comma, DOBJ, right arc, comma, date, and things like that. So that's what it says. Parameterize the left arc and right arc operators with dependency labels like left arc n subject or right arc d object. And the job of the oracle will be to return the correct action from a large set of actions. Now the set of actions become larger, right? If you combine this combination, consider this combination as the action. And is the oracle always right? No, it may give incorrect response. And how to create a good oracle? Supervised methods. So again, for parse trees also, there are many tree banks, and these tree banks will have examples of the input sentence and the dependency relations. So based on that, one can come up with supervised methods, or which actually will play the role of this oracle. Now this one example of neural network based approach for transition based parsing. So here what it says is that, here they use BiLSTM, but one can use any contextual embedding method. So the input is the brown fox jumped over the lazy dog. Okay, so you have this, and you also have the word root. So you have everything together. You pass it through an LSTM, and the BiLSTM representation for each of the words are with you. And at the same time, you also have, so this S2, S1, S0, this is the stack, and B0, B1, B2, B3 is the one that is there in the buffer. Okay, B stands for buffer. So each transition is scored by using an MLP. That is fed the BiLSTM encodings of the first word in the buffer and the 3 words at the top of the stack. So here the first word of the buffer is the, okay, and the 3 words at the top of the stack are the jumped over. So you already have these embeddings created. So you have an MLP that takes these 3 or these 4 things at the input, the first one from the buffer and the top 3 from the stack. And this MLP now gives you a score for the left arc, the right arc, and shift. Okay, and I pick the best transition gradle. So suppose it says, yeah, so if it says that the should be shifted, you simply shift the. So the stack now contains the jumped over the, and B1 is, the buffer contains lazy dog and root. So like that, this can be done. So this is one approach. Simple. You have the representation of everyone, and based on the representations, you take a decision whether left arc, right arc, or shift. For labels, you can do the same thing. You can also predict the label. And there was one more idea here. So let me again check the formatting. So here, the idea is like, suppose you have n nodes, right? And many different trees can be constructed from these n nodes, right? Now each tree will have some edges. So what this algorithm does is, for each possible edge, it predicts a score. Then it solves some optimization to pick the final tree, which is nothing but a collection of edges from the collection of the edges. And for each edge, anyways, the score is there. So what they'll do is, for each word, get the embeddings, and based on these embeddings, for each pair of words, to identify a score. Okay, Now you can view it as a complete graph. There are n nodes and there are n C2 edges, and each edge has a weight. Now from it, you want to get a tree that has the highest score. They pose this problem as the maximum spanning tree problem. Okay, what is a spanning tree? Spanning tree is a tree which will have all the nodes present in it. Okay, and it's a maximum spanning tree that they want. That means the spanning tree. So the first condition is that it should cover all the nodes, and secondly, it should be a tree, and thirdly, the edges which are there in the tree will be the highest among all possible spanning trees that you can create from this one. So this is another neural network based approach, and they said the edges can be labeled using another classifier. Okay, so this is about dependency parsing, and there is some evaluation of dependency parser. So first one is unlabeled attachment accuracy, and second one is labeled attachment accuracy. So what it does is it compares an actual tree, as the ground truth tree, and the predicted tree. And in unlabeled attachment accuracy, you check the percentage of words in input that are assigned with the correct head. It is unlabeled, that means we ignore the labels. And labeled attachment accuracy will compare these, but will also compare the labels which are there. So let us look at unlabeled attachment accuracy. So it says percentage of words in input that are assigned with the correct head. Okay, so for this predicted tree, for the word book, there is no head. I mean, it should be, the head is null. So for book, it is matching with the ground truth. For the word me, the head is flight. Here for the word me, the head is book, right? So this does not match. For the word the head word is flight. The same thing is here also. So this is correct. For flight, the head node is me. Here also for flight, head, sorry, for the word flight, the head word is book. Yes. So here also for flight, the head word is book. So that is matching. So edges are from head to dependent. Then for through, the Houston is the head. Here also the same thing. So we have a match with the ground truth. For Houston, the correct head is light, and here also it's the same. So this is correct. So out of 6, for 5 of them, we were able to match the word with the correct head. So the unlabeled attachment accuracy or unlabeled attachment score becomes 5/6. Okay. Now for the labeled attachment accuracy, we should check that they are assigned with the correct head and the correct relation. So for book, this is valid. For me, it is assigned to flight. Anyways, it was not matching with the head. So here the head is flight, here the head is book. For the word the, it's a head is flight and label is determiner. Here also head is flight, label is determiner. So this is correct. For flight, head is book, label is xcomp. Here it is book, but the label is iobj. So the label does not match, so we'll cross it. For through, it is Houston and label is case. The same is true here, matching. For Houston, the correct word is flight, correct head word, and label is nmod. The same thing is true here. So this has matched. So out of 6, for 4 words, we were able to assign the correct head word as well as the correct relation. So the label attachment score is 4/6. Okay, so this is how the algorithms can be evaluated. Okay, so this was about dependency parsing. For next, we have semantic parsing, and I'll cover it briefly. I mean, I'll cover it very briefly. So semantic parsing actually deals with the semantics or the meanings. So each word in a sentence has some role to play. In fact, that's why they're here. In some cases, the role could be mostly functional because the structure of the sentence won't be complete otherwise. On the other hand, there are situations where the semantic roles will be very concrete. For example, yesterday Christina hit Scott with a baseball. Scott was hit by Christina yesterday with a baseball. Yesterday, Scott was hit with a baseball by Christina. And all these sentences, if you look at, they mean exactly the same thing. So if you do constituency parsing, there this will be same, but they look different, but the meaning is same. And the words which are highlighted here, they contain the same semantic role across the info. So Christina is the person who was the agent or who carried out the action, who was the hitter. And thing or person hit is Scott. That role remained same across the sentences. With a baseball is the instrument that is used for the hitting, and temporal adjunct is when was this done. So the parse trees will look different, but roles will be same. So semantic roles could be of the form like who did what to whom at where. So we'll have some example or some clearer. So it tries to determine who has done something. So that is one role. What was done, that is another role. To whom it was done, another role. When it was done, another role. Where, why, how. So these are some of the roles which could be there in semantic role labeling. Now, it can be used for question answering. If you know it's a who question, then if you know the role, you can have a better answer to that question or more confident answer to that question. Similarly, answering WH questions could be quite simple and easier here, and also it will have the explainability property as well. Then for machine translation also, if you know the sentence and the roles and the word order and other things are different in the target language, you can actually make use of this information in getting the target. Summarization also can make use of it. And these semantic roles are not new, or they are not something which the English NLP community is thinking about. We know something of this sort from our from the grammars of our original languages as well. So there are different vibhaktis, right? Prathama, which essentially says who is the subject, and Dvitiya, which says the object, then Tritiya, which says what is the instrument, and so on. The receiver, the place or from where it originated, and possession, location to address. So this is semantic roles are there in Indian languages as well. So this thematic role I'll skip. So I'll talk about two data sets. One is PropBank and another is FrameNet. So PropBank is a data set where the semantic roles are labeled using some specific restricted sets of roles. The first, one role is called proto agent, which says what is the entity, what is the object, or what is the person or organization that is directly and consciously involved in doing something, okay, in that event. So this person may also cause an event or change the state of another participant. Examples are there in the following slides. And then arg1, which is for the proto patient, it undergoes something that undergoes a state change or which is affected by some action done by the agent. Then there could be some other arguments like who is the beneficiary, what is the instrument, what is the attribute, what is the start point, what is the end point, and so on. So let us look at some examples. So here, suppose we have one example sentence like the group agreed it won't make an offer. So the central word, the main action is the agreement. Who agreed? The group. So this is now becoming the proto agent because what is the group that has the direct involvement, major involvement in this event. So agreement, the major involvement is the group, and agreed with what? It would not make an offer. So this one is arg1. Then if you say usually John agrees with Mary on everything. Okay, who agrees? That is the proto agent, the main subject. And agrees with whom? That becomes the other entity which is agreeing. And what is the object for agreement? On anything. And when does it happen? Usually. So there is some temporal. So in prop bank, you have many such examples, and you also have this kind of labelings saying that, okay, which segment has what level and why that level is given. Here is one more example. Sales fell to $25 million from $27 million. So what fell? Sales. But remember, sales is not something that will fall itself. There are some other events which are causing the sales to fall, right? So that's why sales will come as argument 1. So it's not no volitional involvement. So it's the effect. Sales is something that is at the receiving side for the fall. And 2, it is the end point. To 25 million from 27 million, from where? So they said that argument 3, when I have written, it is for start point, argument 4 is for end point, and arg1 is the logical subject. And then the average junk bond fell by 4.2%. So R2 is extent or amount of volume. So again, we have examples. We have segmented them, 2 different arguments, and for each argument, we have also listed why it is marked as that argument. So similarly, there could be many other things. So here agree, and the word agree can be used in many senses. This is the sense number 1. There could be agree .02, which is sense 02 for agree. Similarly for fall, for increase, and so on. So here, big fruit company increased the price of bananas. So who changed? Big fruit company. It causes an event to change, so it's arg0. The one which experienced the change, that is arg1. And the price of bananas increased in this one. So here we do not have any arg0. Now the question is that if you are given any such sentence and you have to identify what is arg0 or what is the proto agent, what is arg1, what is the proto patient, you should be able to tell that. So again, for this, some classifier, essentially it's a classification task. One can use any classification technique for this purpose. And then you also have some additional predicates like temporal, location, and so on. Next, what people said is that, you are creating examples separately for increase, for fall, for decrease, and so on. But if you look at the words increase, decrease, fall, they are, or rise, they all try to capture similar kinds of things, right? Or if you, yeah, so then is there a way in which we can identify the group of words for which the roles that we expect to see in the sentences in which they appear are expected to remain the same? In that case, you can actually combine all of them, and instead of having one single verb, you can or one single noun, you can have a collection of verbs and nouns and adverbs and call it a frame. And for each frame, you have some properties, okay, not individually for each of them. The price of bananas increased 5%. The price of bananas rose 5%. There has been a 5% rise in the price of bananas. Increase, rose, rise, all are essentially used in the similar context and mean similar kinds of things. So what about the different verbs that mean the same thing? So they typically are surrounded by, some other very common or similar words like reservation, flight, seat, book, ticket, fare. All are possibly about booking kind of stuff. So the words are used in a common sense background information, and this background knowledge is called a frame. So this is a frame. So advance, climb, decline, decrease, diminish, dip. As you realize, they are all very related terms, and the corresponding nouns also will be there. there could be adverbs increasingly. All of them have some kind of commonality in that sense. So they create a frame. And for a frame, you have these properties. For example, there could be a frame called hit target, where the participating verbs could be hit, pick off, shoot, and so on. Now, here you'll have agent and target. Those are most likely expected to be there in every case. And then you'll have also a few optional things, which will be 1 second. Hello. Okay. So yeah, so frame has some lexical units which will list down the words which will invoke this frame. And there are some core or mandatory frame elements. And then there are some non-core, which are optional things. So here are some other example rules, which are a bit more broad. So which is actually a broader list. And the task of finding the semantic roles of each argument of each predicate. The predicate here is the verb. In a sentence, labels are different for prop bank and FrameNet. So here, as you can see, for FrameNet, so these are the roles: item value, range, and these kinds of things. And for prop bank, the roles were arg0, arg1 kind of thing. So roles vary. Yeah, we have an example here also. Here from FrameNet, we have cognizer, target, evaluate, and in case of prop bank, the roles are different. So there can be many ways of doing this semantic role labeling task. One can actually have feature-based algorithm. Suppose we have the sentence like the San Francisco Examiner issued a special edition around noon yesterday. And we want to know what is the role of the phrase the San Francisco Examiner here. Okay. So one feature could be like head word of the constituent examiner. The head word for this part of speech, head words part of speech, which is NNP. The voice of the clause, it is active voice. Subcategorization of the predicate, VP to VBD, NP, PP. So predicate is word, the word here, and it is under the VP. And for VP, the subcategorization is VBD, NP, PP. This one. Named entity type of the constituent, organization. First and last words of the constituent, the and examiner. Linear position of the clause with respect to the predicate. So it comes before the predicate. So before. And the path that you take to come from the word, this head word, to the predicate. So you start with a noun phrase, then you go up. So that is this NP followed by U. Then you reach S. After S, you come down and come to VP, D, VP. And after VP, you come down to this VBD. So this is how you can reach from this examiner to this predicate. So all these things can be considered as features, and they can be vectorized in some manner. And an algorithm can then tell you what is the role of this. And you can also have something like simply you enter the entire sentence here. So the cat slub hacked. So this is the sentence. You have a separator, and then you give the predicate. Okay. Now this is the predicate event here, and you pass it through some encoder, and every layer. So every token now has a representation, and then based on some other, you can pass it to some neural network and get the desired output. So here also it's a sequence, right? So you can also have the BIO kind of encoding here. So there are some recent works also where you have the sentence and you identify the predicate Then there is some transformer which will firstly identify the predicate classifier. So there could be many different predicates, many different candidate predicates in a sentence. So it will identify the main predicate. And by considering that, it will also try to figure out what is the nature of the argument here, arg0, arg1, and so on. And for it can also identify the property, like what is the role that makes it of that type. Like if it is arg0, why is it so? So they have created a network for end-to-end training of this one. This is one. Then people also use it. Now people are talking about semantic role labeling in computer vision and so on. But here the idea is that you have an input, assume a textual input. Every role, every word or every phrase has a role to play. And these roles are mostly from a set of predefined roles. According to prop bank terminology, it could be like arg0, arg1, arg2, like that. Or according to FrameNet terminology, it could be something like the what were those levels? The target, the amount by which it has fallen, and things like that. So essentially deal with the classification task here. And yeah, so that is about semantic role labeling. Any questions?
Sir, these the earlier parsing which we saw, sir, dependency one and the next one and the CKY, they looks like a semi-supervised setup because labels we are working on the labelings, right?
Sorry, say again.
So these parsing techniques, dependency parsing, and then whatever we saw the next and the CKY parsing, in all of these we are working on the labelings. So they are like semi-supervised setups. These all parsing setups.
Not really. Semi-supervised? No, it's not semi-supervised for sure. So in the CQB algorithm that we saw, so here it was a dynamic programming algorithm. So there is no learning involved in that.
Okay.
So yes,
Yeah.
you need to have the rules on the basis of which the decisions were made, but it's a deterministic and there is no learning component there. Number one. Then in case of dependency relations, so it was a supervised algorithm because when you train the system to predict the level or to predict the sage, so that was a supervised machine learning algorithm. And yeah, here also it is a supervised machine learning algorithm because you need to have these levels, this word, this is the level, and so on. Supervised, not semi-supervised.
Okay.
Sir, one question where we use this pre-trained transformer. So what's the input and output, because transformer accepts it has encoder and decoder both, right? So are we using both here?
If it is only a classification, right? Decoder may not be needed.
Okay, so just one.
You get representation for each word, you pass it through a classifier.
Oh, so what will be the input in that case?
The input you can construct from here. So this is one sample input. Yeah, this is the sentence. And then this is the predicate. Then for each token, you predict the level.
Okay. And what's the significance of this arg0 kind of labeling and arg1? And earlier we saw different kind of labeling. So why we are doing these many kind of, what's the extra thing this arg0 arg1 is bringing?
So these are the levels, right? According to the data set.
Yeah, my question is that earlier also we did different kind of labeling, right? Where we had just the arrow and all. So now we are doing this where we have arg0, arg1. So what extra it is bringing?
So it is so here we are not talking about the connections between the different pairs of words. We're saying in this sentence, so dependency parsing says what is the connection between these pairs of words. So here it says in the context of the entire sentence, what is the role that this word is playing?
Okay. So it is per word.
Per word or per phrase? Yes, yes. In some sense per word. But there can be phrases as well.
Okay, got it.
Okay then, so we'll hang up here today. I'll share the slides and I'll also post the assignment in the Teams channel. Thank you for attending.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.